To this sensitivity analysis for LP's webinar. So in this webinar we will do this in three parts. So first part we will introduce how sensitivity analysis could be used and how it is used in AIMMS. The second part will deal with the marginal values, which means of shadow price and reduced costs. So how can you extract them and how can you plot them in AIMMS. And the third part will deal with the right-hand side ranges and coefficient ranges in AIMMS. So first, a little introduction on when do we need sensitivity analysis indeed. So there is two main reasons why we do sensitivity analysis. The first main reason is uncertainty in input data, which means that, well, you have a model and all your constraints are depending on coefficient for your variables and what we call the right-hand side of your constraints. And those values could be something that you measured before and that could be uncertain. So the sensitivity analysis tries to tackle those issues of uncertainty. The second reason is the impact of different policy scenarios that you could have on your model. So how could we perform that on a mathematical optimization model? Well, there is a discrete way of doing it, which is doing it by hand, which means running the model several times with small changes in the input data, for example, but without any idea on how your model is progressing through the constraints. This is difficult to run those kind of analysis and be sure about the output of a change in input data. Or you can do it by doing a post-optimality analysis, so without being forced to resolve the entire model and basically by using the marginal values. So this is a continuous way of doing it because this post-optimality analysis is performed thanks to quantities that are mathematically calculated. So how could we perform those kind of post-optimality analysis? Well, basically by extracting and studying marginal values, which means shadow price and reduced cost, and by extracting and studying right-hand sides, ranges, and coefficient ranges. Okay, so we will start with a small model to begin, which enables us to re-understand the concepts and how it works with shadow price. So here is a small products and chips model. So here you can see this is a two-variable model. So I have vegetable chips and organic chips that I want to produce during one day. And the selling price of those chips are here, so $2 per kilo for the organic chips and $1.5 per kilo for the vegetable chips. And this model is subject to three main constraints. So this model is inspired by the AIMMS optimization modeling book that you can refer to it later. And basically those are simple constraints such as slicing, frying, and packing in that order. And what we can see here, so 385 minutes, 480 minutes, and 330 minutes for the packing constraint are what we call the right-hand side of those constraints. So here is the representation of the model in 2D. So because we have two variables, we can represent that model in 2D. That's why we are working on a very simple model like that. And what we can see in gray here is the solution domain, so which means that every point of this domain could be a solution of our problem, which means that it respects all the constraints that are here. But actually the optimal solution is situated on one of those nodes. So what we can see, just to finish here, the lines are basically the constraints that are here, and the slope of those lines are determined by the coefficient one variables, and the value here on the x2 axis is determined somehow by the right-hand side range. So when we solve this simple model, we could find that the objective function here, well, the optimal point would be 57.5 kilos for x1 and 50 kilos for x2. What we can see as well is that the objective function slope here is determined by those coefficients in front of our variables. So basically the whole question of this webinar is, well, if I was not really sure about the data, the input data of my constraints, would it be a very different optimal solution? Okay, how could this impact my optimal solution and my profit actually? So, for example, if we are taking the packing constraint, if it's not really 330 minutes, but for example 331 minutes, that is the right packing constraint on one day, does the optimal solution change a lot? So what we can see here is that this optimal point is determined, well, by two constraints, which are the packing and the frying constraints. And we call those constraints actually the binding constraints, which means that the slicing constraint here, well, we could get rid of this constraint and the optimal solution will be the same. So what if we change this right-hand side? So this is how we introduce the shadow price, because this is the definition of the shadow price. The shadow price of a constraint actually is the rate of change of the objective function from 1 unit increase in its right-hand side, which means that the shadow price answered exactly to this kind of question. If you change the capacity, the packing capacity by 330 minutes, sorry, to 331 minutes, actually the increase in the objective function value will be known. So I will just show you in AIMMS how could we extract those shadow prices. So here you can see that I implemented the small model in AIMMS software. So we have the X1 and X2, the three constraints, and of course the mathematical program there. So I will solve this simple model. It takes not a long time, and then we could check for every constraint what is the shadow price. So to do that, you can go to the constraint and the data of the constraint. So here the data is 0 because actually the constraint is binding, so it has no value. Okay, and you can go into the edit mode and select in the content to add the shadow price of your constraint into this display. Thus, I access to the shadow price in this data page, and we can see that the suffix to access the shadow price for a certain constraint in your model is this suffix. So here, what I could see is that the shadow price of the packing constraint is $0.33 per minute, actually, which is dollars because it's related to the objective function, and per minute because the right-hand side of our packing constraint is minutes. Okay, oh, sorry, the right problem was this one. Okay, so now small sensitivity analysis that we could do to answer this question is just to increase the right-hand side by just 1, for example. If we do that and we resolve the problem, we could see that the objective just increased by exactly the amount predicted by the shadow price. So if we increase again by 1 minute, we have the pleasure to see that the increase is indeed again represented by the shadow price. So getting back to the presentation, we can see that the shadow prices for every constraint in our model actually are plotted here. Okay, and answering this simple question would be, well, our objective will increase by $0.33. Well, yes, but to what extent can we increase this right-hand side or decrease it? Well, actually, there is a limit which is called the right-hand side ranges. So normally in a real sensitivity analysis, you would study the shadow price, but as well as the right-hand side ranges, because actually shadow prices are local quantities that are that are valid only on the edge of the optimal solution, which means when you modify the model, so I modify the model there by just adding 1 minute to the right-hand side of the packing capacity, I change the model, and thus we are not sure that the shadow price is the same. We will get back to that later, but this gives you a real nice feeling of what is a shadow price for a certain constraint. So the idea now is, could we apply this concept to a variable? So yes, because our variable are subject to some bounds, and those bounds actually could be implemented as constraints. So this is what we call the reduced cost, which is actually the rate of change of the objective function for 1 unit increase in its bound. In our small model, the reduced cost is 0 because actually the two variables are not at one of their bound. One of their bound is 0 or plus infinite. So we do not have any reduced cost. The idea is if one of those variables would be at one of their bound, so the 0 bound, for example, well, we would see appear the reduced cost. So we can do this small experiment in AIMMS by, for example, changing the coefficient in the objective function. So getting back to the model, getting to the coefficient function, and for example, let's say that X2, which are my organic chips, I now sell them $0.5 a kilo. So by doing that, I'm changing the problem and resolving it would lead me to see that my X2 variable now have a reduced cost of minus 0.5. So what happened? Well, actually, the level of my variable is 0 because it's not used anymore. The program has chosen to use only X1. Okay, so this is what happened. We changed the objective function, and now we have a reduced cost of minus $0.5 per kilo. So how can we interpret that? Well, there is two ways of understanding that. Is that if X2, what this tells us on X2 is that if X2 was $0.5 per kilo more expensive, we would sell it. So we would sell it in, so we would use it, actually the program will use it in the optimal solution. If we were bound to sell X2, which is another idea, we would decrease our profit by $0.5 per kilo. So this could be really useful if you are bound to put a certain variable at a certain amount and see and quantify what this impacts your objective function value. So this was for the shadow price and reduced cost, and just for the purpose of the presentation, those are normal interpretation of the shadow price and reduced cost. So it depends on your model and your application domain, but here is some ideas on how can we use the shadow price and the reduced cost. So the basic idea of the shadow price and reduced cost is the cost of a constraint for the system. So we can now know, for example, in our small model, we have different shadow price for every constraint. For example, the frying constraint was 0.17 and the packing constraint was 0.33, which means that the packing constraint was more binding in a certain way than the frying constraint. So if we want to impact our profit in the most beneficial way, we would increase the packing capacity. So it could be interpreted as the marginal price of the electricity as well. So the shadow price associated to the balancing constraint actually on the market, on the electricity market, gives you the price of the electricity, or at least the price of the electricity on real-time based. So this is what we call the spot price in the electricity. So it could represent the value of a raw material for our system. So a raw material that we are using to build a product, for example, would be determined by our model and then we will compare this price of this raw material. We will compare it to the real price on the market for this raw material, and then could determine if it is useful or not, or determine if we should use, this raw material or not. So the value of relaxed and tight and a constraint related to the quality of a product. This is basically quite the same idea than before, but then you know that you have to do a blending problem, for example, so to mix different raw material in order to do a product. And you will be able to determine, well, if I have some tolerances on the quantity of the raw material, I will be able to quantify them thanks to the shadow price and the reduced cost. So overall, the effect of small changing in the capacity, so in the electricity, it's well known. If you want to have the shadow price of a certain capacity, you would so how would this impact on your objective function? But the shadow price has, well, mainly two limits that we must be aware of, even if they could be handled in AIMMS. So the two main limits are, first of all, the degeneracy. So degeneracy happens when you have your optimal solution that is bounded by three constraints in our case, and we have a two-dimensional problem, which means that your optimal solution is some way overbounded, okay? And in this situation, the interpretation of the shadow price is different. Why it's more difficult. So we will use the shadow price ranges, but I'm not dealing with that today in this webinar. And of course, the second idea is the right-hand side ranges to be sure that the shadow price is valid when we are using it. So this is what I will present in the following slides. So in our small problem, so getting back to our small problem, we were studying the packing capacity with this right-hand side here, and we knew that the shadow price was $0.33 per minute, but on this optimal point. So by changing the right-hand side, actually here, basically what we are doing, graphically speaking, is that we are shifting our packing constraint to the right in this case. And what we can see is that if we are shifting our packing constraint, well, the solution domain will increase until this packing constraint is not binding anymore. So here we can definitely see that the frying capacity will be the only constraint that will constrain our that will be binding in our solution. So at this point, actually, the shadow price will change. But on this entire range, the shadow price is valid. We could do the same thing. So we could do the same thing in the other way, okay? And then it happened that we could extract what we call the right-hand side ranges, which means the ranges of the right-hand side where this shadow price is valid. So where we could do those kind of conclusions. So those two notions that we just saw, so the shadow price and the right-hand side ranges, leads us to be able to answer a certain type of question. For example, this is kind of a basic type of sensitivity equation. I want my objective to be accurate within 1%. And let's say that our model is really accurate except this packing capacity, because our packing machine is not really working well every time. So in this situation, we can run a sensitivity analysis on this packing constraint expressly. So, and thanks to the shadow price and the right-hand side ranges, well, we know that you have to know your packing capacity within a 5.75 minute range at least in order to be accurate within 1% on your objective function. So what is the calculation? 1% of the objective function is 190, which was the amount of our objective function value. So this is 1% of the objective function, and that we divide by the shadow price, and we know that our right-hand side, which is there, so the number of minutes that a packing machine is take, shouldn't be more than 5.75 minutes, if this is the only right-hand side range that changed. Another type of question, which is most often the case, how much an increase of 100 minutes on packing, here for example, will improve my profit? Well, according to the right-hand side range, we are sure that the shadow price will not change. And so we could say basically that it's $33, which is $0.33 here times 100 minutes. So the objective function will increase by $33. And so we can compare that to, for example, the price of the machine cost or the price of the policy change that we are about to make. Okay. So this was for the right-hand side and the shadow prices. But we could ask ourselves the question, if there is a way to do a sensitivity analysis on something else than only the right-hand side. So, for example, we would be interested to do a sensitivity analysis on the coefficient in the objective function. So, the question that we want to answer, the same as the shadow price, but on the variables this time, what if X1's selling price was not $2 per kilo, but between two values, let's say 1.9 and 2.1? Well, in order to tackle this issue, we could use what we call the coefficient range, which is a mathematical quantity that is extracted and calculated by AIMMS directly in the output of your LP model. The coefficient range of decimal variable is the range of possible value its objective function coefficient can take without modifying the optimal solution. So in our case, in our small example, I could plot those ranges. So, for example, in X1, I will do the same trick as before. So when you have the data page, you can edit the data page by double-clicking on it and updating the content. Okay. And because I specified here in the property that I wanted to have the coefficient range of this X1 variable, then in the data page, I can access those two values. Okay. Yes. There is a problem there. Oh yeah, because I changed the objective function. Sorry for that. So let's get back to the right objective function. Otherwise, it won't work. Okay. So, sorry for this interruption. So for the X1 variable, we will update the content here by searching for the smallest coefficient and the largest coefficient that are possible in our model. So we are adding, we're adding those two values. Okay, and what we can see here is that the value of X1 is indeed 58.3 in our model because we changed the packing capacity, okay? And the smallest coefficient is 1.2 and the largest coefficient is 3, to be compared to the nominal coefficient, which is, in our case, 2. Okay. So this is quite powerful in terms of knowledge, because then we would know that if we are changing our coefficient in this range, we won't change the optimal solution, which means that we won't change here the value of x1 and x2. So in our small example, if I just update the constraint and then resolve the model, yeah. So we know that our two variables here, yes, 57.5 and 58. So sorry for that. Thus, the optimal solution isn't changed. So here I try to represent that graphically. So graphically, what does this mean? Because it's not really logical in terms of optimization. Well, actually, we are on the edge of the solution domain here. And by changing the coefficient in the objective function, okay, what we do is just that we are turning around that point the slope of the objective function, which means that basically those are our variable values, and those values are unchanged during this process. So this is represented by those coefficients. So how could this be useful? Well, actually, we can answer this question quite straightforward and say that the optimal solution will be unchanged. Thus, if the optimal solution would be unchanged, we could track the profit by just multiplying the price with the quantity that are here unchanged. Okay. Another type of question that we could answer is how much should I be precise on X1 selling price, thus on my production plan, for example. Well, in our small example, on the production plan, not a lot, because, well, you could have a 50% increase or decrease and the production plan will be the same. But maybe a lot regarding your profit. Just be aware of that because, well, your profit actually depends now just on the selling price because the quantities are fixed, because in this case there is no change in the optimal solution. And so your profit will follow this function. Here, the selling price of X1, of course. So now let's try those kind of values on a larger example. So I wanted to show you by the end of this webinar a nice example of a power system balancing optimization model. So in this model we have four types of generators, so hydro, biomass, coal and gas, which is typically a system that we could have. And those generators are subject to maximum power and available. So here the hydro power plant could go until 500 megawatts, but not more than that. And a certain price on the megawatt hour that it could deliver. So hydro is a bit cheap and gas is a bit expensive, but because gas is available every time, so we can use that in peak hours. So here I plotted the demand. So this is a typical demand of a small system with those four types of generators. And we can see that the demand is in megawatt. Here you have 1 gigawatt, okay? So this could be the mean of our values. And here the values are plotted for every hours. So sorry, I do not plot the hours there, but every line is an hour in the day. So this is an entire day. This is the night, okay? Here this is the morning, so increasing in the morning, then the entire day, and in the evening you have an increase as well. This is a typical load curve in electricity. So now in getting into AIMMS, I implemented this small model. So with the generation variables that are here, so we have 4 variables for each hour in a day. The electrical demand that is there, that we can look into it, and this is the same demand that I've plotted, okay? And the mathematical problem. So our problem here is to fill out fill out the demand with all those generators when they are available, but fill out this demand in an optimal way. Okay, so we have what we call a balancing capacity, which means that the sum of all the generation of our generators should be equal to the demand for each hour. Okay, so this must be optimized, okay, as well as a capacity constraint, which means that, well, every generation mean could go more than its maximum power, okay. So we can go into the web UI in order to see what happened. So here I plotted the demand, so you can see for each hour, so there is the legend. When solving the entire model, we can have this kind of input, which is what we call the generation dispatch. So each block here represents a generator, so the hydropower plant is used the first, and then we have the biomass and then the coal. And in the peak hours, we could have access to the gas. So what is interesting is that for every generator, we have, as I shown, a capacity constraint. And we can extract the shadow price from this capacity constraint thanks to AIMMS. So for example, here, the hydropower plant, the shadow price of the capacity constraint, because the hydropower plant is there binding, this capacity is binding because it is at its maximal power. So the shadow price is $15 per megawatt, okay, so which is the right-hand side, okay. The right-hand side of the hydro is 500 megawatt, okay. So this is dollars per megawatt, and $15 per megawatt, which means that if I increase the hydropower plant maximum power by 1, I would increase the objective function by $15, okay, if I do it by 2, etc. So what we can see as interesting is that when we are in the night, okay, so this is in the night, and the shadow price is lower than when you are in the day, of course, because here what happened is that if you increase the hydro capacity by 1, well, you will decrease the amount of gas that is used. And because gas is really expensive for our system here, it will profit our objective function. Okay, now we can plot as well what I explained before, so the marginal cost of the electricity for this small system. So actually this is the shadow price associated to the balancing constraint. And in this case, we could see that the price of electricity would be $35 an hour, $35 per megawatt hour in our case. And in the peak hours, of course, it's more expensive. Okay. Then maybe, well, what could be a very interesting graph here is, well, the balancing constraint right-hand side. So here in black, you could see the demand, and then the red curve here is the highest right-hand side coefficient, and the blue one is the lowest right-hand side coefficient. So this just gives us actually, well, this tells us that if we change the demand in those two bounds, the production plan won't change at all, which is quite powerful. So which means that if my demand, if I know my demand within those ranges, okay, well, the production plan will be exactly the same, okay. So I won't change the amount of power, I won't change, sorry, my production plan. Okay, and maybe the last graph. So here we can show coefficient ranges per generators, because we have coefficient ranges, of course, on the capacity constraint of every generator. Okay, so getting back to the presentation, to conclude this this webinar, so we saw three types of notions, so the shadow price, the right-hand side ranges, and the coefficient ranges. So mathematical implication is that, well, if the shadow price is 0, we can say that a constraint is not binding for a system, which means that we could get rid of this constraint and the optimal solution would be the same. And mostly the economic, with quotes, interpretation would be the cost of a certain constraint for our model. This is related to a constraint identifier in AIMMS. Right-hand side ranges are the shadow price validity domain, which enables you to do a sensitivity analysis on your solution regarding the change on the input data, regarding the right-hand side range. And the coefficient ranges that means that the optimal solution isn't changed, and you could access that with a variable. So one main limit of all those notions is that those are local sensitivity analysis and are concerning are associated to only one constraint at a time, which means that those kind of sensitivity, you can do it only one constraint at a time or only one variable, one coefficient, sorry, at a time, which limits a bit our understanding of our model. So to go further, you could go with what we call the parametric programming, which is basically to change two right-hand side range or two coefficient or mixed problem at the same time, and then see the changes in your optimization model. So here, to go further, you can see the optimization modeling book online from AIMMS, which go into details what I've just explained in this webinar. We could treat in another webinar the shadow price ranges and the value ranges, of course. And well, regarding the topic of sensitivity analysis and uncertainty in input data, we can study the stochastic programming and robust optimization. For that, you may refer to this webinar, which is on the AIMMS website, dealing with uncertainty in optimization-based decision support application using AIMMS. So just to finish, the next webinar will be held by Chris Cope on access management in AIMMS WebWise, so how you can manage access right for a group of individual people for the WebWise. This will be held in the 22nd of February, and I hope to see you there.